So welcome to this lecture. This is the first lecture on physics-informed neural networks. So I'm going to be introducing physics-informed neural networks in this lecture. Before I get started on physics-informed neural networks, I just want to recap what Sid talked to you about last week. And he talked about the importance of partial differential equations, and PDEs really are the fundamental building blocks that we use to describe and understand, many different scientific phenomena. From, this very smallest of scales, using, for example, the Schrödinger equation to model the dynamics of atoms, to the very largest scales, and using, for example, Einstein's equations to model black holes. PDEs are also really important to understand phenomena that happen here on Earth. So, for example, the Navier-Stokes equations are really essential for understanding how the climate evolves and the fluid dynamics of the climate. And then what's amazing is that some biological systems can also be described by PDEs. So, for example, the reaction diffusion equation can be used to model how the patterns on animal skin evolve over time as they grow. So this is why we place a lot of emphasis on PDEs in this course. And physics-informed neural networks are a way to solve differential equations, or a way to solve problems related to differential equations. And I'm going to show you exactly how PINNs, physics-informed neural networks, can do this. So yeah, this is the first of quite a few lectures on physics-informed neural networks. We're now really into the main body of the course, where we're getting into these kind of new scientific machine learning techniques that we've been talking about so far. So yeah, how does this lecture look? So first of all, I'm going to give you a very high-level description of what physics-informed neural networks are, a really simple description. Then, hopefully, if it works, I'm going to try and do some live coding to show you just how easy it is to train a physics-informed neural network in PyTorch, just in a few lines of code. And then I'm going to really justify why we use PINNs and all the different applications that you can use them for. And so it turns out you can use them not only just to solve differential equations, so carrying out forward simulation tasks, but you can also use them to carry out inverse problems. This is, discovering underlying parameters of a system given some observations of that system. And you can even use PINNs to start discovering the PDE itself, so the terms of the PDE. So PINNs are a really flexible framework and really interesting field of research to study. So by the end of the lecture, you should be able to explain precisely what a physics-informed neural network is and how to train one, and all the different kind of applications that we use PINNs for, and all the different tasks that you can use a PINN for. Okay, so what is a physics-informed neural network? So before I describe exactly what a PINN is, I want you to have a think about how you might use a neural network to solve a differential equation. So Sid last lecture talked about all these traditional numerical methods we have, so things like finite difference methods, finite element methods. And he talked about the pros and cons of those methods. But PINNs are fundamentally different. They use a neural network to solve the differential equation. So I just want you to start off the morning, just talk with your partner about ways that you could use a neural network to either solve a differential equation or help you solve the differential equation. So I'll give you a couple of minutes, and then I'll see what you've come up with. Just have a quick discussion. It's a very broad question. So. Okay, so it's just a very quick discussion. So can anyone give me a hand of a way that you thought of using a neural network to solve a differential equation, to carry out simulation? Yeah.
Well, we give it as inputs the initial conditions.
Yeah.
And maybe some numerical approximation of the one flashing or something at the initial point.
Yeah.
And then as an output is supposed to produce, or it is supposed to produce the result, and we use some other method to obtain the result. And then there.
Yeah. Yeah, it sounds so. To repeat, so you would have a neural network that would take in the input to the network would be these initial conditions. So by the way, this is an example of solving the wave equation with the acoustic wave equation here and some initial conditions. And this output here is the output of a finite difference solver. So you might have a neural network that takes these as inputs and then tries to produce this simulation as output. And you train it maybe based on lots of examples from finite difference modeling, for example. Yeah, in a supervised manner. Yeah. Yep, definitely. Any other ideas? Yeah.
I know, like maybe one could skip the part of something generically because like you have the data equation itself, and maybe you can somehow like take a difference between what the neural network produces and what the data equation tells us what it's supposed to be.
Yeah.
Maybe you could work with that.
Yeah, this is a really good idea, and so this is very similar to what PINNs do. So the idea is to, instead of generating lots of data to train the network, which is very expensive in general, if you have to remember, I was saying in the introduction to deep learning, we need thousands, millions of examples to train deep neural networks, and that could take hours or days to compute on a traditional simulation. So if we could use the wave equation directly to train the network and minimize or penalize the difference using the wave equation, that would be better. Yeah. So that's a great start to thinking about physics-informed neural networks. So let's now start to think what a PINN is. So I'm gonna take an even easier differential equation. This is an ordinary differential equation, and it's the equation for a damped harmonic oscillator. And so this is a canonical problem in physics, and it just models a mass on the spring. What is the displacement of this mass as a function of time? And we know that the displacement u here is a function of time, just obeys this differential equation where m here is the mass of the oscillator, mu is the coefficient of friction, so it's some dampening term, and then k is the spring constant. And so we get this, depending on the kind of regime of the oscillator, you can have overdamped and underdamped and critically damped regimes. But this is the underdamped regime where the oscillator slowly decays over time. So we have this sinusoidal function with an exponential decay. And so we know, in general, to be able to solve a differential equation, we have to give it a unique set of initial conditions and boundary conditions to give us a particular solution. So the appropriate ones here are to say the mass is going to start with a displacement of 1 and a velocity of 0. That allows us to uniquely, and in this case, analytically solve the ODE. Okay, so how are we going to try and solve this equation using a neural network? And what I mean by solving is we want to be able to compute this function. Let's just assume that we don't know what it is analytically, because for the vast majority of PDEs, we don't know what the analytical solution is. So PINNs are very, very simple. The underlying idea of a PINN is very simply to approximate the solution directly with a neural network. So we say my solution, u of t, is approximated by this function. Remember, neural networks are just functions that fit to data. So it's a neural network function that takes in the coordinate t, or the time value t, and has some free parameters theta. So just to be very explicit, we typically, for PINNs, we start with an MLP. This is usually the model that we start with. And so the MLP has in this case, a single scalar input. It's the time value. And then it gives you a single scalar output, and that's the prediction of the displacement. So one question already is, how is this solution that we get from this technique different to the solution from, for example, finite difference modeling? Can anyone tell me? Just by the way that we're framing the problem here. Okay, so I'll tell you. What we're doing here that's fundamentally different to finite difference modeling is we're making a functional approximation to the solution. So the output of the PINN is a function that we can query at any point in time, and it will give us its approximation of the solution. That's not the case when we run finite difference modeling. What we get from finite difference modeling is a discretized version of the solution. We get the solution on the value of the solution on the mesh of points that we use. So one key property of PINs is this idea of them being mesh-free. They're a mesh-free approach. We don't need a mesh to compute the solution. Okay. So then the question is, what loss function do we use to train the PINN? And this is where we put in this information of the differential equation, as you were suggesting, into the loss function. So we have two loss functions. One is called, or two components to the loss function. One is called the boundary loss, and one is called the physics loss. Sometimes it's called the PDE residual. I'm just going to refer to it as the physics loss going forwards. And it's very simple. What we're saying is, with the boundary loss, that the neural network should match whatever our initial conditions are. So let's take the first, this boundary loss has two terms. Let's take the first term. It says that the output of the neural network at t equals 0 should just equal 1. And so that's exactly saying, you know, this initial condition, the displacement starts at 1. The second term in the boundary loss is to say that the derivative of the network with respect to t should equal 0. And again, that's just saying that the velocity should equal 0. That's our initial condition. Then the final one, which is the most important, is this physics loss. And what this does is it computes the residual of the underlying differential equation. So we take our neural network and we just evaluate all of the gradients required. So, you know, the derivatives with respect to time that are required to compute this left-hand side of the differential equation. And if this solution exactly matches, you know, is a true solution of the differential equation, what is the value that we expect this to be? If neural network is a true solution. Yes, 0, yeah. You know, that's what the differential equation says. So we try and make sure that this residual is as close to 0 as possible. And if it is, then the neural network is giving us a true solution. Now we have to evaluate this residual at many different points in the domain. So we sample over many different time values to make sure that across the entire solution domain, this residual of the differential equation is obeyed. So you can think of the boundary loss as, you know, asserting the boundary conditions and making sure that the solution is unique. And then the physics loss is making sure that the underlying equation is obeyed at all points in the domain. And here's what happens if I train a fully connected neural network using exactly this loss function here. And what you're seeing is the gray curve is the exact solution, and the blue curve is the neural network's fit or the neural network's prediction of the displacement as a function of the training step. Now I'm also plotting a couple of points here. So what I'm plotting the boundary point. So this is just t equals 0 here. This is the boundary point that we're matching to in the loss function. And we just have one point in this case for this single 1D equation. And then the green points here are these what we call physics loss training locations, or we also call them the co-location points. So these are the time points here that we sample the physics loss over to make sure that the differential equation is obeyed at all points in the domain. So this is a super key slide to really understand every element of the slide. Everything that we're going to talk about in the remaining lectures on PINs is going to come back to these core ideas of how we train PINs and how they're defined. So has anyone got any questions before we move on? Yeah, go on.
So the train of inside computation domain that we're looking at similar
Yes.
to the worded numerical.
Yes,
And if we were to sample from outside that domain, totally different.
absolutely. Yep. So really good observation. If I take this trained neural network that I've trained here, and I give it a time coordinate that's outside of the domain, it's very likely that that's not going to obey the underlying solution because it's outside of the training distribution of the network. So the generalization of neural networks is still an issue here. Yep. So we're going to talk about that in the next lecture as well. Yep. Yep.
Different training steps, like difference between training steps.
Right. So we're training this network just how we train a normal neural network with gradient descent. So we take the gradient of the loss function with respect to the weights, and we take a step. So what I'm showing here is the prediction of the network as a function of training step.
in every step we would use all the training locations, like all the TIs.
Yes. Yeah. So So unlike what we normally do with neural networks, where we use mini batches and we do like small batches of training points, what is more often the case in PINNs is just to use full batch training. So you give it all the points at every training step. So all of these green points and all the orange points in this training example are being used every step. Yep. Yeah. Any other questions? Yeah. Yeah. So you don't have to. So and it's good to compare when you're training PINNs. And it often depends on the type of problem that you're solving as well. To me, it makes more sense because it makes the problem more well posed, in that you're making sure that the PDE loss is consistent everywhere, and there needs to be like a deeper level. There needs to be communication. Like we need to be able to, without this boundary point here, we could learn any solution to this differential equation, and it could start anywhere in for example. So somehow we need to communicate this boundary point across the in time forwards and solve it causally. So having all these points can help do that rather than just randomly sampling. Yeah. We'll talk about that more as well. Yeah. Go on.
Yeah, the way it seems to learn from left to right. You know what I mean? So like,
Yes.
does this come from physics or from?
Yeah. I think it comes from what I'm talking about when we need to communicate or propagate the boundary conditions forwards in time. We don't know what the solution is here until we've learned what the solution is before it, to constrain the value, like to solve the equation forwards in time. But I mean, in general, it's very difficult to understand the training dynamics of physics-informed neural networks. This is actually quite difficult. So this is my empirical observations, but to analyze it mathematically is a really interesting topic as well, to think about the training dynamics. So yeah, we'll talk about that as well coming up. So yeah. Okay. Yep. Yep. Yeah, so we're going to talk next lecture about extensions of PINNs. And so physics-informed neural networks is an entire research field, and there's a lot of clever ways to make them generalize better, to speed them up, to improve their limitations. So I'll talk about this. Okay. I'm just going to check the chat as well, because it looks like we have a question. Oh no, it's just a suggestion. Okay. Okay. So as I mentioned, these green points in the domain are known as co-location points, and we sample them through the domain. And one other thing that I haven't talked about so far is these lambda values. And you can see that they are just weights that we apply to each term in the loss function. And what we do is that we just consider them as hyperparameters that allow us to scale or balance the contribution of each of the terms in the loss function. And so in practice, this is really important to make sure that the PINN converges quickly. If you set, for example, the boundary weights to be very, very low, then you might just learn a different solution that's not the true particular solution of the differential equation. Okay. So I showed you a PINN for the damped harmonic oscillator. But what makes PINNs so powerful and why they're such a popular or heavily researched field today is that they are actually a general framework for solving partial differential equations. So I can take this idea of just using a neural network to represent the solution of a differential equation and train it on any differential equation I like. So we can set up PINNs in a more abstract way and say, given some PDE, and I'm not being specific about what PDE is, and some boundary initial conditions. So we can just say that the PDE in general is just some differential operator that's applied to the solution that gives us maybe some function as output, where we have some domain in some d-dimensional space. So for example, a 3D problem with x, y, and t, for example. And we have some boundary operators. We might have k of them, for example. We might have a initial condition on the velocity and on the value of the solution itself. Equals, again, some boundary function here evaluated on the boundaries of the domain. This can define precisely our PDE or boundary value problem that we want to solve. You can also incorporate time here into X. So I haven't explicitly said that time is here, but it could be incorporated into this vector. So PINNs train a neural network to approximate the solution to the PDE by directly approximating the solution. So this is a functional approximation of the solution. And we use these two loss terms that I just described. So we have the boundary loss, where we have a separate loss term for each boundary condition, each k boundary condition. And we have a physics loss that minimizes the residual of that underlying differential equation. Okay, so to make it more concrete for you and to show you an application of a PINN to a different partial differential equation, I'm just going to consider the Burger's equation. So this models fluid flow. And this is the viscous Burger's equation. So we have some viscosity parameter nu here. And u here now represents the speed of the flow. And we're thinking about the flow just through a 1D section as a function of time. So the solution here is the flow wherever you are on that section, and then a function of time. So we set up these initial conditions. We just say that the starting flow is some sine function in X. And then we have some boundary conditions saying at the edges of the domain, the flow should be 0. So what we're actually modeling here is the fluid flow through a pipe, for example, where the fluid starts with a sinusoidal distribution of its velocity. Okay, so then we say, yeah, the solution is approximated by a neural network. And then we do exactly as we did before. We have our boundary loss here, where we have now 3 terms in our boundary loss, which are asserting each of these 3 boundary conditions. So, neural network across all points in X, but at time equals 0, we want to match to the negative sign function. So we need to sample sample many possible values of X when we're evaluating this term. Then this term says at X equals -1, but for all values of T, we should make sure that it's 0, and for X equals +1, the same thing. And then the physics loss, we're just evaluating the residual of the full differential equation, sampling over all possible values of X and T in our domain. Okay. So let me show you a picture of what that looks like. This is the same loss function again. But what I'm plotting here is the black points and the green points. The black points represent where we sampled the boundary loss from. So when we did the 1D harmonic oscillator, we only needed 1 boundary point because it was 1D, but in higher dimensions, you need to sample, the subspace of the domain. So we're sampling across the edges of the domain here for these boundary loss here. And then the green points here are where we're sampling the physics loss. You can also see that we're not doing a uniform sampling anymore. We can also do a random sampling in the domain, and actually random or quasi-random sampling can actually improve or help the convergence of PINNs, and we'll talk about that coming up. And yeah, this is actually plotted here is the solution of the PINN. And so what you can see is, again, this is the fluid flow through a pipe, and we started with a sinusoidal fluid flow. And what's interesting about the Burger's equation and what makes it nice to study is that as time goes forwards, the fluid starts to form a shock, and you start getting flow that goes one way and the other way, and you get a shock in the middle. And so this is quite an interesting problem to study, especially when we're using numerical methods, because we can start to get really big discretization errors where we have these discontinuities in the solution. And what's nice to see is if you plot the kind of exact solution against what the neural network predicts after it's been trained, it does somehow model this shock fairly well in its solution, and gets quite a good match to the true solution. So this is a plot that was taken directly from Rice's physics-informed neural networks paper, which is kind of the seminal paper on physics-informed neural networks. To be more specific about kind of the setup that they used, and it's important to understand kind of these fine details. They used 10,000 co-location points in the physics loss here. And they used not uniform sampling, but this thing called Latin hypercube sampling, which is pseudo random sampling. And then they had 100 boundary points sampled, along the boundary here. The network they used was a fully connected network, nine layers, 20 hidden units. So that turns out to be 3,000 free parameters that we need to fit this flexible function to the solution. And then we use a TANH activation function and a second order optimizer. So not just gradient descent, but quasi Newton optimizer. So one interesting thing is the activation function. So can anyone tell me why they chose to use a TANH activation function here instead of, say, for example, a ReLU activation? Yeah. Yes. Yeah, exactly. So the answer was that ReLU always gives positive outputs. That's true. What we typically do when we do neural networks for regression is we don't use an activation for the final layer, which gives us the opportunity to have negative values. But the real reason why we would use a TANH is that it's a continuously differentiable and smooth function. So why is that important? Why do we need a continuously differentiable function or activation function? Yep. Yeah, exactly. We need to be able to evaluate the second order derivative here of the neural network with respect to its inputs. So if I used a ReLU activation, what would that value be? Remember, a ReLU activation is a piecewise linear function. Yeah. So the gradients of the piecewise linear function, the second order derivative is 0 of a neural network that uses a ReLU activation function. So that's a really important thing to understand. It's often overlooked when we train neural networks. They're actually making piecewise linear approximations if we use ReLU. But if we use a TANH activation, then we have in general, a continuously differentiable function that we can fit. So you don't have to just use TANH. You can use other kind of smooth approximations of the ReLU functions. There are these swish functions, for example, or others that you can use. So I've been hinting that PINNs is an entire research field by this point. And if you look at the number of publications that have the keyword physics-informed neural networks in them, you can just see that the amount of papers published on PINNs each year has just been growing very, very quickly. And it's a whole research field. There are so many extensions of PINNs, and we'll cover some of them in the lectures coming up. But if you really want to get into physics-informed neural networks in more detail, you can have a look at this review paper, which is a fairly good comprehensive review of all the research landscape on PINNs to date. It's actually quite interesting to note that the kind of basic concepts behind PINNs, so this idea of using a neural network to approximate the solution and then train it using this residual of your differential equation. These basic ideas can be found in papers going back all the way to the 1990s, for example, Lagares and others. But the paper that is most well known for PINNs is Rice's paper, and this is the kind of seminal paper which re-implemented and extended PINNs using modern deep learning frameworks and showing that we can train deep, fully connected networks and other networks to solve these differential equations. Okay. So hopefully I've described to you a high level what a PINN is. So now I'm going to talk in much more detail about the training process of training the PINNs. There's quite a lot of factors that I haven't talked about or I've left out so far. And I'm going to hopefully in this section talk to you about or do a live coding of a PINN in PyTorch to show you how easy it is to train in PyTorch. So let's think about the training loop of a physics-informed neural network in more detail. So let's go back to this harmonic oscillator example, which is, a simple example to think about. Again, we have our boundary loss and we have our physics loss. And so this is how the training loop would look if I just write it down as a list. So we would first start by just sampling our boundary points and our physics training points or our co-location points. So note the orange point and the green point here. Then we would compute our network output. And then the important thing is we need to evaluate the derivative of the network with respect to its inputs. So these dn by dt and dn by dt squares to be able to compute this physics loss and also the boundary loss here. Then that allows us to actually compute the value of the loss function. But then we need to do another step where we need to take the gradient of the loss function with respect to the neural network parameters in order to update the parameters to learn the solution. So the key question here is, how do we compute the gradients that we require? So, dn by dt and dl by d theta. So can anyone tell me how we would compute those? Or even if they're available. Yep. Yeah, so in general, the neural network here is just a mathematical function. Remember, it's just a bunch of linear operations plus some activation functions. So we can write down analytically the derivative of the network with respect to its input. That's something we can actually analytically derive. If you had a pen and paper, you could do it. And as I described in the introduction to deep learning lectures, we don't actually do that in practice. We can just use the auto differentiation and backpropagation as an efficient way to compute those gradients. So the important thing is we can use autodiff not just to get the gradients of the loss function with respect to the weights, but also we can use autodiff to get the gradients of the networks outputs with respect to its inputs. Same algorithm, same auto differentiation can be used. So let me just show you how we would use autodiff to get both of those gradients. And let's just assume that the network is a MLP, so a fully connected network that has this form. And we use the chain rule when we were differentiating the loss function with respect to the weights to be able to evaluate that gradient. So we can use very analogously the chain rule to now compute the gradients of the network with respect to its inputs. So a different gradient, but very similar. So we just note that the neural network function is just composed of these vector functions. And we just use the chain rule to find out what the derivative of the network with respect to its inputs are. And you can derive this analytically, like I said. I don't have the time to do it today, but this is an exercise that you can go away and do. And so we can just show that the derivative of the network with respect to time is this expression here. Okay. So then how do we get, once we've evaluated this derivative, how do we get now the derivative of the loss function with respect to the weights? That's the next derivative that we need. So we can just, to do this, we can use autodiff, and we can simply just think of computing these derivatives of the network with respect to its inputs as extending our computational graph when we're using auto differentiation. So autodiff works by creating a graph of all your operations and tracking that graph, and then backpropagating through that graph to give you your gradients. So this gradient here, the derivative of the network with respect to time, is just some extra computation. You can just think of it as an extra computation, which just extends this forward graph of the network. So this derivative just depends on the activations G and H, and it passes them through some functions which are derivatives of the activation functions and times them by weights. So we can just plot that as an extra part of our computational graph, which then allows us to compute the final output of the graph, which is the loss function. So once we've extended our computational graph, then we can just call autodiff on the entire graph, this full combined graph, to backpropagate through from the loss function to backpropagate through it to get the gradients of the weights. So this is the kind of key realization, is that we can recursively apply autodiff to first get our gradients of the network with respect to its inputs, create a new graph, and then get the gradients of that graph with respect to the network's parameters to update the parameters themselves. So this is how it would look in some pseudocode of in PyTorch. And so, like I said, you can in practice just use autograd to get these gradients. And so you would have t here is our time coordinate, theta is our parameters of our network. We get the prediction of the network given the value of t. And then we compute our first gradient, which is our derivative of the output of the network with respect to time. And we can just use autograd to get this. We also need the second order derivative with respect to time to evaluate the physics loss. And the key thing we do in PyTorch is we do this thing called create graph equals true. And that extends the computational graph so that we can then differentiate through it again when we call autograd the final time to get the gradient of the loss function with respect to the weights. Hopefully this makes sense. Does anyone have any questions on how we get these two gradients? Okay. So now we have everything we need to actually train a PINN in PyTorch and to actually code up a PINN. And so I'm going to attempt to do some live coding for you. So for the people in Zoom, I'm just going to stop sharing and try and share my screen, my Chrome screen. Okay, so hopefully you can see that okay. So what I have here is a Jupyter notebook. And I've got a lot of the code here is already filled in. I'm just going to be adding a couple of lines, the key lines for training the physics informed network. So we're going to be using PyTorch. So everyone can see this, okay? Yeah. We're going to be using PyTorch. So I'm just going to import the relevant libraries. Okay, so again, we're going to be training a PINN to solve this damped harmonic oscillator. I've already told you about the differential equation. There are different regimes. We're going to be focusing on the underdamped state here, where we have this kind of decay of the solution. Analytically, you can actually show that the solution has this form. So it's a cosine function as a function of time, damped by this exponential factor. And if you're interested in kind of deriving this, I would have a check out of this blog post. It's very, very useful for understanding. Okay, so the first thing we're going to do is just simulate the system using the PINN. So we're going to try and solve this differential equation. So I've got a couple of kind of pre-computed or predefined functions here. This is just a function that computes the exact solution given some parameters. So here omega 0 is the base frequency of the solution, which just depends on the spring constant and the mass. And again, delta here determines how much dampening we have, and it depends again on the coefficient of friction and the mass. So given these two values, we can figure out what the exact solution is. And then this is just a class in PyTorch, which just defines a standard fully connected network. And I'm not going to describe this. I think we already covered this in the tutorials with you. So hopefully this is familiar to you. Okay, so we're going to train the PINN with exactly the loss function I've been describing in the lectures here. And we're going to be using Torch autograd to get these gradients. And so this block here is the main block that we're going to be using to train the network. And you can see already that it's not many lines of code. Like in PyTorch, we can do this with 10 lines of code or so. And it should be very similar to, or it should look very similar to you when you've been training normal neural networks. And so we start by just creating a neural network, a fully connected network, which here just has 32 hidden units and three layers. Then we set up our optimizer, and then we have a standard training loop here where we're getting a loss function and we're backpropagating through the loss function. So this is standard PyTorch code. So what I'm going to do is what I need to do is define the boundary loss and the physics loss in this code. And so first thing to do is to define this boundary loss. And so the first thing we need is to define the point that we're evaluating the boundary loss at. And so for this problem is just a single point. So we're going to say that t at the boundary is a torch dot tensor, and it's the value 0. So we're going to be passing t equals 0 into the network. So the other thing we need to do is that because we need gradients of the network's output with respect to this input coordinate, we need to tell PyTorch to start tracking the computational graph that is created when we use this tensor. So this just says track the graph so that we can later get gradients with respect to this tensor. So we do this requires grad property here. I'm also just going to change the shape of the tensor so that it's just appropriate for feeding it into the network. We also have to define our physics training points. So these are the co-location points that we use to evaluate the physics loss. So it's going to look very similar, but now we need more than one point. We need to sample the points across the domain. So I'm just going to do a simple uniform sampling of the points from 0 to 1, which is our domain that we're going to be solving it's the domain that we're going to be solving the differential equation over. So where are we? Yeah, and we'll take 30 points. And again, we're going to need to require gradient. And we're going to make a nice view of the data. Okay, so now we've got our points that we're going to feed into the network. Now we need to compute these loss values in our training loop. So the first thing we need to do is the boundary loss. And the first boundary condition that we want is that the solution should be 1 at t equals 0. And so we're going to say, first we need to compute the solution using the PINN. So we just call the PINN with our boundary point. And then we want the first loss, to be the difference between the network's prediction and 1. And we're going to square this. So very simple first loss function. The only other thing I'm going to do is squeeze it, which just turns it into a scalar value, which is appropriate for PyTorch. Okay, so then the next term, we now need to bring in autograd to get the derivative of the network with respect to its input to make sure that the velocity of the oscillator is 0 at the start. So how do we do this? So we use autograd. So we say du by dt equals torch dot autograd dot grad. This is our core kind of gradient computation using autograd. And we want the derivative of the output with respect to the boundary point. So torch dot autograd makes it very easy to get these gradients, and this is just how we define it in PyTorch. So an important thing to note, so this is the documentation for torch.autograd.grad. And what it actually does behind the scenes is compute the vector Jacobian product. So in general, U here is a vector function of t. And what this autograd tool does is actually give you a vector times by the Jacobian of that vector function. Now, if that's confusing to you, don't worry. I'm going to be explaining what autograd is in much more detail in the second half of the course when we talk about differentiable physics. But for now, all I need to do is just specify what that vector is that I'm computing the vector Jacobian product with, and that can just be a vector of 1s for now. So we'll just do torch dot 1s like the solution. The final thing we need to do is this create graph flag, which I explained before, makes us build the computational graph so that we can then differentiate through it again when we evaluate the gradient of the loss function. And I know that this returns a tuple, and we need the first element of the tuple. So this should just be a vector, the same shape as U. It just has the gradient of U with respect to t. And then we can just go ahead and compute our second term in the boundary loss, which is just the difference between U by dt and 0. So we're saying the velocity is going to be 0 at time equals 0. We're going to square it, and we're also going to do the squeezing as well. Torch dot squeeze. Okay. So we're nearly there. Now all we have to do is compute the physics loss, and we're going to use exactly the same autograd tools to get these the extra gradients that we need. So the first thing to do is now to compute the PINN, not at the boundary points, but now at the physics points, so across the domain. So t physics. And then I'm going to copy this line and paste it twice, and I'm going to pass the physics points instead of the boundary points. Like this. And what's neat about autodiff is that we can, again, recursively apply autodiff to our computational graph. So for getting the second order derivative with respect to time, we can just pass in, this object here, which is tracked by the computational graph. So, our velocity vector. So now we've got all the derivatives that we need to compute the physics loss. And so we can just do that by doing loss 3 is the mean across all the co-location points of, and now we just type in the underlying PDE residual. So this is, let's just go back to what it looks like. It's the mass, which we're just assuming in this case is 1 to make it simple, times by the second derivative plus the coefficient of friction times by the first derivative plus k, evaluated on the network. So we can just do this. Du by dt plus mu times by du by dt squared plus mu times du by dt plus k times by u. And then we want to square this to make sure that we're doing the squared error. So I'm just going to double check this to make sure that I've not made any mistakes. So I think this should be fine. This should be fine. That looks fine. That looks fine. Okay, so I think it's okay. So let's give it a run, and if it's not, I'll try and debug it. So the rest of the code here is just plotting, as training progresses, it's just plotting the PINN solution. So we're querying the PINN at a set of test locations, a much finer sampling density than the physics loss. Yeah, and it looks like it's working. And so, yeah, this is the animation that I showed you in the lecture. So as the PINN converges, we start to converge on the solution. And these green points here are those physics points that I use to train, and the red point is that boundary point. So anyone have any questions on the code before I go back to the lecture? Yeah.
I have one question. When you sum up the loss in the end, you have like loss equals, and then you loss 1 plus lambda 1
Yeah.
plus 2 plus lambda 3 plus 3.
Exactly, yeah.
And why is that? What's weird about the
Yeah.
lambdas are basically the boundary.
Yeah. So
Yeah.
yeah, so you can choose. The important thing is you just have a relative balance between the terms. It doesn't matter what the magnitude of the terms are, or it does, but when we use Adam, it does this automatic scaling, so we don't have to worry about the absolute magnitude. But it's an important question to think about. I chose these, by the way, by just doing the experiments myself and changing these values by hand. But there are better ways to do this, and I'll talk about that next lecture. Yep. Yep. Torch backwards. Yeah, you could. This is just a PyTorch thing. That if when I call torch dot backwards, it doesn't give me a vector of the gradient. What it does is it does the backprop through the computational graph and accumulates that gradient inside of the leaves of the tree. This is just the way that PyTorch is framed. Yeah. Yeah, so we do need to do create graph equals true for here because we need to differentiate through this derivative when we're getting the gradient of the loss function with respect to the weights. So the final torch.grad call is this loss dot backwards. So we need to build that graph to be able to differentiate through it when we update the weights. Does that make sense? Okay. Yeah. Anyone else? Okay. So now I'm going to try and switch my screen again. Stop share. Okay. Right. So what's important is to think about the computational cost of evaluating these derivatives. Like I've said that they're available and we can compute them analytically or equivalently using auto differentiation. But the cost of getting these derivatives can be quite high. So if you just think about the computational graph, that we build when we add these extra computations to compute these gradients with respect to the inputs, you can see that these computations roughly double the size of the computational graph. If I go back to this expression here, this expression here has roughly, without going into it in detail, you can see it has roughly the same computational cost as the forward pass of the network just to evaluate this function here. It's doing similar things, right? It's timesing vectors by weight matrices and passing them through derivatives of activation functions, kind of the same computational complexity. So we can actually, more precisely, you can derive that the time that it takes to, given some vector function here, the time it takes to compute the Jacobian vector product is approximately this omega, so a constant value times by the time it takes to compute the forward pass of the network only, where omega is some value between 2 and 2.5. And to really understand that derivation, you can have a look at this reference here. So it sounds good, like we can compute it in roughly the same amount of time as the forward pass, but we want higher order derivatives when we're training PINNs normally. We want second order derivatives or even higher order derivatives when we're evaluating this physics loss. And so this grows, cost of evaluating this higher order derivative grows exponentially with the value of n. So we get this omega to the power of n kind of computational scaling. So when you're training PINNs, what you'll normally find is most of the time spent training it is not in the forward pass of the network, but actually when we're computing the gradients. And this is kind of a key kind of limit or kind of limitation of the computational cost of PINNs. There's a couple of other important considerations, which I think we've pretty much talked about already now. Yeah, the lambda values really significantly affect convergence, and often they're a key choice to define them properly. We also have to make sure that we have enough co-location points in the domain to make sure that we constrain the PDE residual precisely across the whole domain. And enough is quite hard to define precisely. When we do finite difference methods, finite element methods, we have very clear convergence criteria on what the sample spacing should be, for example. You might think, for example, here we have basically a sine wave, and so we'd want to make sure that the sample points are below the Nyquist sampling rate. That would be a kind of a sensible start to make sure that this converges. And similarly, we need enough boundary points to make sure that the learned solution is unique. We can sample these co-location points randomly or uniformly if we like. And as someone pointed out at the very start, PINNs, even though they have this kind of clever physics loss inside of them, they're still a neural network at the end of the day, and they still suffer from all of these error sources that I talked about in the introduction to deep learning lecture. So they still have approximation error. If this neural network is not flexible or expressive enough to represent this true solution, it's not going to converge to that solution. They have estimation error. If we don't choose enough co-location points, we'll converge on a solution that's not minimizes the true expected loss. And optimization error, like even though we might have a neural network that can give us a solution, this might be a very complicated objective function for the optimizer, and it still might not converge. So yeah, next lecture we'll talk about how we can get over some of these limitations when we're training PINNs. And if you compare this to kind of finite element, finite difference methods where we have like analytical bounds on the convergence, this is a kind of very different setup. The final way to look at PINNs before I move on and talk about the applications of where we use PINNs is to reframe PINNs from a machine learning perspective. And I think it's really interesting, given this course is AI in science and engineering and the very intersection of these two fields, it can be very useful to look at these techniques from a pure machine learning perspective. So from a mathematical perspective, we've set these neural networks up to solve partial differential equations. They're a functional approximation to the solution. But what can we say about PINNs from a machine learning perspective? If purely from the perspective of training a neural network, what's interesting about this loss function? Can anyone make some observations about the loss? I'll make it a bit easier for you. Imagine if we just interpret this boundary loss as like a supervised loss. You know, we have the neural network here and we're matching it to some labeled training data here, like 1 and 0. We're saying that it should equal these values. So what's different about the physics loss? Yeah. Yeah. It's more like a, so you said it's more like a regularization term, which is exactly right. So the physics loss here, it doesn't need any labels. You know, if we're thinking about this from a supervised learning versus unsupervised learning framework, the boundary loss has these labels, what we want the solution to be. The physics loss, all we give it are these time points, these inputs to the network. And it evaluates this loss function based on just those inputs of the network. So from an ML perspective, we can think of the physics loss as an unsupervised regularizer, which is asserting prior knowledge. It's giving us this inductive, it's not an inductive bias, but like a regularization term that pushes the types of solutions that the network learns towards solutions that obey the differential equation. So this is a really nice way to think of it from a machine learning perspective. It's a regularization term. So let me just make that like super clear. This is a different way that you can train PINNs, where instead of having this like specific boundary loss, you can just say, okay, what if I just have a bunch of observations of the solution? You know, these orange points here. Then if I just train like a standard neural network with a supervised loss on those observational points, you can see that the network, you know, fits the data very well within its training range. But as soon as I query the network outside of that training data points, the solution just flattens out and is really poor approximation. So now we think of the physics loss as basically adding a regularization, and we extend the co-location points further outside of the training points, and we can start to learn a more general solution, with the caveat that if we test it with a time point that's even further outside of those co-location points, it's not going to perform very well. So hopefully that makes sense from a machine learning perspective. And then if I step back to an even higher level and we think about these three broad categories that I talked about in the first lecture of ways to incorporate scientific principles into machine learning, we're very much on the left-hand side here. We're talking about changing the loss function of the neural network. We're just using in a PINN of a standard neural network architecture. And we're adding some scientific understanding to the loss function to improve the performance of this network. Okay. So we're going to take a break, and then I'm going to come back and talk about the applications of PINNs and how we can extend them to solve inverse and equation discovery problems. So yeah, let's take 5 minutes. I explained to you at the start what a physics-informed neural network is, and I showed you how to train it. I did some live coding. So now I'm going to talk about the applications of PINNs, so all the different types of scientific tasks that we can use physics-informed neural networks to solve. I've been focusing so far on simulation tasks, solving the differential equation. But what I'm going to try to show you is that we can also use PINNs to solve inverse problems and also equation discovery problems. So let's just go back to the kind of key scientific tasks that we often want to solve. And this is a slide I showed in the course introduction. This is just an example using the wave equation. So the example of seismic simulation, but you can take any PDE and there would be similar tasks associated with it. So forward simulation is a task of, you know, given some input conditions to the system. So for example, a velocity model of the Earth and the location of an earthquake in the Earth. Can I predict the outputs of that physical system? So in this case, what is the amplitude of the seismic waves that propagate through that media? So we can say B here, the outputs of the system just depends on some model of the system. Typically, this is a PDE and some inputs to the system A. So an inverse problem is to try and do the reverse. It's to say, given some observations of the outputs of the system, so in this case, the wave field, the seismic amplitude, can we invert for the underlying structure of the Earth or where the location of the earthquake is? And then the final task is equation discovery. This is the task of not only discovering input parameters, but actually understanding the underlying differential equation or model behind all of this this dynamics. So in this case, maybe your observational data would be the wave field, the source location, and also the Earth model itself. And given all of that data and observations, can we invert for the underlying differential equation, which in this case is the acoustic wave equation? And so what I'm going to try and convince you in the last part of this lecture is to say that PINNs can solve all of these three categories of tasks and not just simulation tasks. So I've got just one more example of PINNs doing simulation before I move on to those other tasks. So this is some work that we did where we solved the wave equation. So that equation that I just showed you using PINNs. And so the task here is given a velocity model. This is just describing the velocity of the Earth. And in this case, I'm just assuming the Earth is just a very simple horizontally layered structure. And given a source location in the middle of that, can I predict how the seismic waves propagate through that Earth model? And so this is actually what it looks like if I run a ground truth simulation using finite difference modeling. And it's really interesting to look at how these wave fields evolve over time. We get a lot of complicated physics that happens. So we get a general kind of outwards explosion of the source. But then as we hit these interfaces in the velocity model, we start to get these reflections at each interface. We also start to see compression and expansion of the wave field or of the wavelet, depending on the velocity that it's going through. So it squashes up when the velocity is slow. And we get lots of other interesting effects as well that can occur in wave physics. So in general, this is a really interesting kind of problem to model and to see if PINNs can model this sort of function. And this function is much more complicated than the kind of single sinusoidal function that we were looking at before. So how do we do this? Well, the setup is exactly the same as I've been describing. So here we have a fully connected neural network, where the output is just a scalar. It's just essentially the pressure of the seismic wave, which is what I'm showing in this plot here. And then the input to the network, we're going to solve this in 2 dimensions in space, and then we have the time. It's a time varying problem, so we have time as an extra input to the network. Now, to make sure that the network learns the boundary conditions, for this example, what we did is we just matched the network to a very small number of finite different steps, just for the very first 0.02 seconds of the simulation. So basically just this red box here, we took as example supervised examples of the solution to match the network to. And then we sampled the physics loss using collocation points throughout this whole space-time domain. So all the way up to time equals 0.2. So here's the results. What I'm plotting here is the PINN solution here. So immediately you can see that the physics-informed neural network is able to model the solution, which is really interesting to see. Not only that, it doesn't just get the general outwards motion of the wave field, it also models these reflections, which is, it's just learning to model these reflections based on minimizing that PDE residual. It hasn't seen these reflections in the training data in the boundary conditions that it was given. So that's really cool to see. And then what I'm also plotting here is the output of a naive neural network. So what is this network, or how is this naive network trained? So it's very simply trained by only using the boundary loss and not the physics loss. So this naive network just uses this first term in the loss function here. And it's interesting to compare these 2 solutions. And so the naive network clearly models the boundary data very well, where it has training points. But where it doesn't have training points, it kind of captures the idea of this wave field moving outwards, but doesn't understand about these reflections in the wave field. So you can really see why the physics-informed loss is essential for getting the correct dynamics here. Okay, so here are some of the kind of more numerical details of this network. So in this case, someone was asking about whether we use full batch. So in this case, I used mini batch sampling. So I did randomly sample 500 points in the domain every training step, and in the boundary as well. it's quite a large network, so it has 10 layers and 1,000 hidden units. So this is a fairly big network to be able to model this sort of function with this complexity. It's using a soft plus activation, which is a continuous version of a redo, and an atom optimizer. Now the big limitation here, and this is often the biggest criticism of PINNs, is the time it takes just to run or to train this network. And this took 1 hour to train on a GPU to get this solution. Now, if I compare that with finite difference modeling, how long do you think the finite difference solver took? Just have a guess. Yeah, it took like 30 seconds to a minute. So this is completely not competitive with finite difference modeling in the raw version, in the raw format of a PINN. So I'm going to be explaining how we get over that problem in the next lecture and how we speed up PINNs to make them more competitive. I'm also going to try and justify why PINNs are still useful for inverse problems and equation discovery in the next slides. Okay, so let's move on to using a PINN for an inverse problem. So again, let me just explicitly say what the inverse problem is, and I'm going to be talking about this same example using modeling seismic waves through the Earth. I have the wave equation, and I have some observations of the wave field here. And what I want to invert for is this underlying velocity of the media, or maybe even where the source location is as well. So how will we do this traditionally? Traditionally, we would frame one way to solve an inverse problem is to frame it as an optimization problem. And we just say that we have our observations B and we have some forward model of the system given some guess of what the underlying inputs are. So this is a guess of the velocity model. And we just minimize the difference between our predicted outputs and the true observed outputs. And if F is differentiable here, if this is a finite difference solver, which is differentiable, we can just use gradient descent on this subjective function. So how are PINNs different? How can PINNs solve this inverse problem in a different way? Okay, so I'm going to explain how we do it. And what we do is very simple. We just change the loss function that we use to train the PINN. So it's a very simple change that allows us to solve these inverse problems. So again, here's the loss function for solving forward simulation. We've already looked at this before. Where here, this is the general form of the loss function, but here the differential operator might be the wave equation, for example. Okay, so if we're going to solve the inverse problem, what we do is we say, in general, we have access to these extra observations of the solution. And so what we're going to do is we're going to add an extra loss term here, where we say, where we have an observation of the solution, we're going to match the neural network output to that observation. So it's an extra supervised loss that we can add to the loss function. So that's the first change that we do. The second change we do is we say, okay, in general, we probably don't know what the boundary conditions are of the problem. Like, let's just assume that we don't have access to that. We just have observations of the solution. So we get rid of the boundary loss. And then we keep the physics loss the same. So we sample lots of points in the domain, just like we did before, and we evaluate the PDE residual. Now, the one other key change we do is we say, okay, well, so this differentiable operator, it has some underlying parameters that we want to try and invert for. These are the, for example, in the wave equation, it's this velocity model here, this C as a function of X. So to be able to solve this inverse problem and estimate what these are, the very simple trick is just to say, okay, these are just going to be extra free parameters that we're going to train inside of our global training algorithm when we're training the PINN. Like, jointly when we're learning so we're going to learn these underlying parameters, phi, for example, jointly when we're learning the values of theta. So you can imagine as the PINN trains, it's not only like simultaneously learning to solve the model forwards, it's also learning the underlying parameters at the same time. It's doing some kind of joint optimization of the problem. So this is kind of cool. This is very different to how I framed the inverse problem before, where here we're just solely focusing on optimizing the underlying parameters and we're not learning the solution. We're just differentiating through a solver. So yeah, it's a very interesting way to think about solving inverse problems, and this can be computationally competitive with a traditional algorithm using gradient descent. Because we don't have to evaluate this expensive forward solver anymore. We're just training a network to fit the data. So we don't have an expensive forward solve in the inverse algorithm. So here's an example using, again, PINNs for the wave equation, but this time we want to understand what the velocity model is. So let's just assume that we have, so this example is a vibrating plate. And what we do is we just vibrate the plate and we measure the displacement of the plate as a function of time. And this is used in non-destructive testing, for example, to investigate whether there's cracks in the plate or any sort of perturbations in the plate. So you can see as this wave is like propagating through the plate, there's some anomaly here which is causing reflections. And so we want to investigate this a bit further. And so given these observations, so this is real data, by the way. This paper is actually taking real data of this vibrating plate. So given these observations, these measurements of the displacement here across the domain, we're going to train the network to match those. And then we're going to also add this physics loss in here, which has the velocity model here. And we're going to assume that we don't understand what the velocity model is of this plate. And instead, what we're going to do is we're going to say, okay, instead of knowing what the velocity is, we're actually going to approximate it with another neural network, which has extra free parameters phi. So we can do that. We can just say velocity is a function of x. It's just approximated by some additional neural network with some free parameters. And when we train the neural network, we're going to jointly optimize theta and phi at the same time. Does that make sense to everyone? Yeah. Okay. So this is the result. So what's happening is when the PINN trains, it slowly starts to fit the solution. And this is the output of the solution network here. And at the same time, it's training that velocity model network to learn the velocity. And we can query that velocity network at any point in space, just like we can query the solution network. And this is what it predicts as the underlying velocity. And you can see it's learned to find this crack in the plate, and it shows up as a perturbation in the velocity model. So I'm going to show you I'm going to go back to my live coding, and I'm going to show you how to do this with the damped harmonic oscillator. And we're going to learn what the coefficient of friction is of the oscillator. And again, I'm just going to show you how easy this is to do in PyTorch. So let me switch my screen and go back to my demo. So this is our second task. We're going to use the PINN to invert for the underlying parameters. So we have this loss function where we don't have the boundary loss anymore. We still have the physics loss. And now we have this extra loss where we're matching the network's output to some observed values. So I need to first just create some noisy observational data that we can use in this data loss. So this is just the code for doing it. And what I'm doing is sampling a bunch of random points in the domain. And I'm using the analytical solution to get the values, but I'm also adding a bit of Gaussian noise to those observations. So I'm assuming that they're noisy. So now this is the same training loop that we had before. And I just now need to adapt this training loop so that I treat the coefficient of friction, the coefficient of friction, mu here, as a learnable parameter. So I need to jointly optimize over mu and the weights of the neural network. So we have to start with an initial guess of what mu is. That's how we kind of start the gradient descent algorithm. So I'm just going to start with an initial guess that mu is just 1. Coefficient of friction of 1. Now I'm in my loss function, I'm going to need the gradients of the loss function with respect to mu to be able to update it. So I need to make sure that this is a tensor that requires gradients, so that I can auto-differ it. The other thing I'm going to do just to help PyTorch is just to define this as a parameter. This is just a wrapper that just allows the optimizer to work well. It doesn't do anything other than that. And then I need to add mu to my optimizer, my PyTorch optimizer, so that it knows to optimize this in its gradient descent loop. So I'm going to create the optimizer by just copying the optimizer above. And I'll just paste it in here. But originally we were just optimizing the PINNs parameters. So now we need to add the mu value as an extra parameter to the optimizer. So we just do that by just converting this into a list and then adding or appending mu to that list. So this is telling the optimizer when you're doing, gradient descent, optimize mu as well as the PINNs parameters. I've already copied and pasted the physics loss into this block. And so the last thing I need to do is define the data loss. So this should be very simple. So I'm just going to compute the PINNs solution at the observed time coordinates. So this is this TOBS tensor here. Where are we? Yep, and then we're going to just say that our second term in the loss function is the mean squared error of u minus the observed. So these are the noisy observations of the solution. And we're going to square it. So I think this all looks good. So now we can just retrain the PINN. And so what I'm plotting here is the noisy observations and the PINN solution as a function of training step. And I'm also plotting the value of mu as the network trains. So remember, we're jointly optimizing the solution and the underlying parameter at the same time. And depending on how many observation points we have, so basically how well posed this inverse problem is, is there enough information in our observation and data points to be able to solve the equation and also estimate mu? Depending on how many points there are, it depends on how well this converges. But in this case, it converges well. So we get a nice fit of the solution. And you can see that we started with a guess of mu equals 1 here, and the optimizer initially overshot and thought it was much higher, and then converged nicely onto the solution. Okay. Any questions on this before I move back to the slides? Okay. Okay, so here's one other example of using PINNs for inverse problems before I move on to the final application of PINNs. And this is to carry out cardiac activation mapping. So this is a completely different use case of PINNs. Here, the goal is to be able to characterize the heart better. And in particular, when your heart beats, the activation of the heart travels as like a wave across the heart. And you can actually map the time at which the activations across the heart occur. And the underlying equation here is the Eikenau equation, and it tells us the relationship between the velocity across the surface of the heart and the time it takes for that point on the surface to activate when the heartbeat occurs. So in general, it's a really useful medical diagnosis to be able to understand this velocity model, the velocity of the heart, to look for any issues with your heart. And so the goal is basically, given observations of the activation times across the heart, can I understand what the underlying velocity of the surface of the heart is? So we can just make this for now just a simple 2D version of the problem where we just have a velocity model that looks like this. This is just a simple toy model for now, and we can actually plot the activation time that it takes across the heart here. So this is the activation time given this velocity model. So what we're going to do is just use a physics-informed neural network to fit both the velocity and the activation times at the same time. And we're just going to use a physics loss here where the neural network approximates the activation time and also approximates the velocity here with these theta and phi weights. And we just match the neural network that's approximating the activation time with the observed time points that we have. So these time points in the domain here. And so what you see, this is the exact solution, and this is the result of the PINN. So the PINN is able to accurately approximate these activation times and also get a fairly good inversion of what the underlying velocity structure is. So this comparison here is if we just train that naive neural network with just the observational times and not the Eikenau equation residual. And you can see it does a much worse kind of interpolation of the velocity without that understanding of the physics equation in the loss function. You can also compare it to just using a Gaussian process to interpolate these data points, and also a linear regression. And it's clear that the PINN with this extra regularization in its loss function is the better model here. Okay, so in the last 5 or 10 minutes, I'm going to move on and say how we can actually use PINNs to start discovering the underlying differential equation itself, rather than just these parameters of the equation. So here's the setup we used for solving inverse problems with PINNs. We said we jointly optimize the weights of the network to simulate the problem, but also the underlying parameters of the differential equation phi. So the question now is, well, how do we actually learn D, this differentiable operator, rather than just some parameters of the operator? So what we're going to do is we're going to say, okay, we're going to assume that D is composed of many different differentiable operators. And we're going to build a library of these operators. So we're going to say our PDE could contain any combination of these operators. So, for example, the partial derivative of the solution with respect to x, with respect to t, the second order derivatives and their combinations. And then we make the assumption that the differential operator can just be represented as this lambda matrix here. So this is a matrix of coefficients multiplied by this library vector of different operators. So for example, if we were going to represent the damped harmonic oscillator in this way, we would have this library of operators and this coefficient matrix, which in this case is just a row vector. So you can see here where we don't need the operator, we'll just set a coefficient in that matrix to be 0. So we only need the first 3 coefficients in this library. And then the goal of learning the equation then turns to turns into a problem of learning these coefficients of this lambda matrix. So this is how we would frame the loss function and train the PINN to do equation discovery. Yeah, we would have, instead of the differential operator, we would replace it with this lambda matrix times by our library of possible operators. So this in general is a harder problem than just solving inverse problems. Inverse problems are already hard to solve when you have, one second, yeah. They're already hard to solve when you have a lot of, when you don't have enough observational data. So this is an even harder problem to do a regression over all of these operators. Yeah.
Does this need assuming some linear combination?
Yeah. So we are assuming it's linear combination if we use this matrix times operators vector, but you don't have to assume that. So if you knew that there was nonlinear terms, or you could include nonlinear terms inside this library. So you could have u times by dx or dx times by dt, for example. So depending on the kind of space of possible differential equations that you want to be able to model, you choose that library to suit. Yeah. Yeah, that's typically the way it's done, but there are other ways to approach it as well. But so what I'm getting at is that this space of possible differential equations, it grows like exponentially. It's a huge space of possible. If you imagine all the combinations of all these operators, that's absolutely massive combinatorial space to search. So this is actually a really hard problem in general. And what we typically have to do is to assert some regularization or prior on the coefficients of the differential equation. So so for example, we assume something like sparsity. We say we want to find a differential equation that has the minimum number of operators possible by, for example, adding an extra regularization term in the loss function that says, you know, the lambda values should be sparse. They should tend towards 0. And this helps make the problem converge and be more of a well-posed problem. Other than that, we just fit in the same way we do with an inverse problem. We have observations of the solution and we just fit the network to those observations. And this is, once we fit those observations, then we're regressing the gradients to get what the underlying equation is. Any other questions? Okay. So this is a paper that did exactly the process that I just described. It came out in Nature Communications a couple of years ago. And yeah, they're doing exactly this. So they have a data loss where they're matching the network solutions to some observational data. Then they have the physics loss, which is minimizing the PDE residual, but using this library of operators and trying to learn the coefficients of those operators. And then it adds some sparsity regularization to try and minimize the number of coefficients that we use. And it's trained by doing like a alternating training where they first learn the weights of the network. So they first fit to the solution data, and then they do a step where they learn the coefficients. And this seems to be better than just doing a joint optimization. So yeah, this is an example from the paper. This is an example of PINNs discovering Berger's equation in the kind of sense of doing a linear regression on the coefficients. So their input data here were just noisy measurements of solutions of the Berger's equation for different initial conditions, as you can see here. And just given those observations and their assumed library of operators, they were able to discover coefficients that gave a very close approximation to the true PDE at the bottom. Okay, so we've covered quite a lot. I've explained to you what PINNs are and how to train them, and I've also showed you that we can use them across forward, inverse, and equation discovery problems. Really important thing is that they're mesh-free, so they give you a functional approximation to the solution rather than just a discretized version. And so there's a direct approximation to the solution. So next lecture, I'll talk about the limitations of PINNs and all the many possible extensions that people use the PINNs are extended by. So, yep, I'll see you next lecture. Thank you.